This is another example of an iterated integral. This time the integrand is e to the x over y. This is another situation where we probably won't be able to evaluate the integral in the prescribed order. We could think about integrating e to the x over y with respect to y first, but this seems difficult. If we evaluate this in this order, the antiderivative we would have to start off with is roughly e to the 1 over y dy. X is a constant, so it doesn't really matter in terms of anti-differentiation in this case. Like I said, I don't know how to do this. You could look this up on Wolfram Alpha or something to see if it's possible, but it doesn't seem like it in any reasonable way. So we suspect that maybe if we change the order and integrate with respect to x first, it'll be more doable. And in fact, I can see that when I look at the integrand, if we think about integrating x first, this is just like e to the x with a constant 1 over y, which doesn't really matter. Integrating e to the x, very easy. So let's switch the order. Now, as usual, when we switch the order of integration, we can't just literally reverse the integral signs. We do have to appropriately redescribe the region here. I'll start by saying the region that we care about is described by the following inequalities. The inner bound here gives y bounds, so this says that y ranges from x to 1. And the outer bound here gives x bounds, so x ranges from 0 to 1. Let me draw the boundary curves given by these inequalities. For example, one of the boundary curves is given by y equals 1, when I take this inequality and generate an equality expression. Y equals 1 is just the horizontal line with height 1. Likewise, this one gives x equals y, which is y equals x, which is some kind of line like that. Those are the y bounds, and then down here I get an x equals 1 equality. That corresponds to this vertical line, and then x equals 0, which is the y-axis. So the region we care about is bounded by these two blue lines and these two red lines. Because y is above x and below 1, that tells us that the region we care about is this triangle right here. So this is the region we want to redescribe in order to change the bounds. So we ultimately want to rewrite the iterated integral so that we're integrating x first. In order to integrate with respect to x first, on the picture here, this amounts to fixing a y value and determining the appropriate bounds in the x direction. Fix a y value, determine the appropriate bounds in the x direction, etc. In other words, we're integrating over slices like this first. It looks like for any fixed y value, the lower bound in the x direction is given by this red curve, which was x equals 0. So the lower bound here will be 0 with respect to x. The upper bound is going to be given by this blue line. This blue line has equation x equals y. Because we want an upper bound for x, that upper bound will be an expression in terms of y because it depends on the height here. And that expression is y. So this comes from x equals y. Now we've integrated in the x direction, so I've accounted for variation this way. What we need to do now is get the y bounds, and the way that we do that now that we've integrated in the x direction is we take the region here and squash it onto the y-axis. In other words, you project this region onto the axis that we want to integrate over. When we do that, we would get an interval like this. The lower bound here is y equals 0. And the upper bound here coincides with this top blue line, which is going to be y equals 1. So our y bounds are 0 to 1. And there we've correctly changed the bounds to integrate with respect to x first. From here, this is a straightforward single variable integration problem. We just have to be careful because initially, now that we're integrating with respect to x, I'm treating this y as constant. So the antiderivative here, this is e to the x with a coefficient of 1 over y. The antiderivative with respect to x is going to be e to the x over y, but then I have to divide by the coefficient here. Dividing by 1 over y is the same thing as multiplying by y. And I'm going to evaluate this at my upper and lower bounds, which are x equals y and x equals 0. When we plug in y for x, what do we get? We'll get y e to the y over y is e to the 1. And then minus, plug in 0 for x, e to the 0 is just 1. So this is minus y. Easy integral to do. Integrating y from 0 to 1 just gives you 1. So in the end, this will be e minus 1. And we are done.